So thanks and welcome everybody. So I'm gonna give a bit of a presentation on the prioritizr like R package that we have developed together. But also I wanted to in the beginning give a bit of a kind of just a structural sense of you're gonna see quite a bit of text on the slides. Like I usually don't use that much text on slides, but I thought it might be a good idea for this group, especially when you want to maybe dive deeper into some of the topics or some of the components that I'm going to talk about, so that you actually have it all in one document, so you can look at the references or some of the definitions. So that's really the main reason why the PowerPoint is set up the way it is today. And then we also have like a code section later on that I'm just going to walk you through. And so that's pretty much the structure for today. But what I really want to do and how I like to start my presentations is point out who is really involved. And so it's not just me, so I'm just presenting to you. But what you see on the screen, it's what I would say it's the core team of folks that have been or are part of the prioritizr like ecosystem, if you will. And the biggest image we have, and also the person that's up front there, is like Jeff Hansen. Like he is a person that started this package, I think, back in 2017. So, and it's really the driving force in terms of data code and analytics in this space. So that's really the brains behind prioritizr. So again, like I'm presenting to you today, but just keep in mind that's mostly Jeff's work that has driven this forward, at least for this package, and also is still driving it. So there's quite a bit of active development too, which is exciting. So we always make good progress and add new features to prioritizr. And so that's also a kind of call to folks here. If you have any things as you explore or like interact with the R package, just open an issue on GitHub and post in there. We're usually trying to respond within a day or so. And we're always happy to listen to the community to see what works well, what doesn't work well, what could be improved, and what other things we might want to add. But anyway, so let's start with probably something that we all know, but it's kind of good to just ground us all into why we do the work that we do. So as we have seen, and there's a lot of evidence now that biodiversity is in severe crisis, so we have quite a bit of decrease in biodiversity across the globe. And so what we then see is like how can we address it and how can we address it in a meaningful way? Because as we probably also all know, it's the whole thing of making decisions. And so I put conservation decisions here, but it's really decisions on land use management, if you will. Because even though we originate our work in conservation, the like tools like prioritizr, they can really be and should be used for land use planning more broadly, but in our case, it's like a conservation lens. And important components are, so conservation is place-based. It usually has or takes like facets of biodiversity or nature into account. And we often, or most of the time, work in resource limited or with resource limited constraints to implement our actions. And so how can we actually make meaningful progress or have meaningful insights first, and then make meaningful progress to actually help nature thrive? So what we usually think of here is like a lot of us work in the space of data science. So we create statistical models, do statistical analysis to get a better understanding of what we see down there in the bolded yellow is, what has been, and what will be. So like it's really a lot of quite fundamental components of our work that then helps us to get a better sense of what is actually on the landscape and how do things change over time. And then when we go or like kind of want to contrast that or how that builds on this work in terms of going to decision science, it's really the whole, so what do we do with that information, or what to do, what actions to take? And down there, I put in the conservation of operations research. So that's really where the insights we gain from data science can really help us in the decision science space. And so what we kind of think about there is how can the data that we generate or interact with in the data science world help us make better or better informed decisions? And so you can see on the bottom of the right side, we have the systematic conservation planning space, and that's really where we developed the prioritizr package. So then for a bit of an introduction to systematic conservation planning, and this is one of the slides that I mentioned before, where there's links to some previous work. So there's lots of good reading that you can do. But then for our purposes, it's really kind of a bit of an abstract of what is systematic conservation planning. So it's really the framework of how to evaluate ongoing management and how we can prioritize actions and monitor the effectiveness. And crucial components there is that it's the whole component there that you can see a bit of an illustration on the right. It's a structured approach. So we have objective-driven analysis or projects, then ideally stakeholder inclusive. And that's also related to what Tong was mentioning before in terms of it's great that we have analytical capacity or ability in some folks, but how to actually connect it more to decision-making folks too. So that's part of what we wanted to do with the prioritizr package. I know that's still fairly technical audience, but we have also taken this step further to then wrap like web interfaces around prioritizr to make it even more accessible. But it's really the whole point is that stake and right holders should be and really need to be included in this whole process or framework. And a big component also that's very much in line with what we've heard before from Jody and Tong is the transparency and reproducibility. So prioritizr is open source, and we try to stay as much as we can with things that are also open or open source that then plug in or can be used with prioritizr. So again, that in this schematic here, number 9 is selecting priority areas for conservation. This is really where packages like prioritizr can help a lot. Now, next, I wanted to just give you a brief overview of some of the terminology that's used quite commonly in systematic conservation planning. So one here is planning units, and you can see like some examples on the right. So it is kind of it's discrete spatial units, and usually what we want to think about is as we think about management, like one unit is managed independently from another one, and what we have often as examples is we have cadastral data, so like property data. We could also have like counties or some bigger unit that might make sense. We also use more computationally easy, let's say, data types like rectangles on the bottom right, or if we want to have a more kind of realistic representation of kind of nature, maybe it's a hexagonal component, but it's really discrete units that then we can do analysis on. That's kind of the main thing for planning units. Then next part would be features. And what we in especially the conservation space usually do, it's some facet of biodiversity. So you can think about like some species information, or a few of the examples here is also like some carbon sequestration potential or different habitat types, like those kind of components. What I would say the main go-to pieces when we talk about features. So features are really something that's representing nature or like some natural phenomenon or like on a spatial extent. And we can intersect this information with the planning unit data that I mentioned before. Then next up, we have targets. So for each of those features, we actually want to set certain requirements, and I'm going to show you a bit of an example later on. But we really want to get a sense of so how much of a feature, let's say, how much of a species is present across the study area that's made up out of those planning units? And then what do we actually want to say set aside? And so when we have like a target for at least say 30% of the range of a bird species I want to have in my solution. So that's what we define as the target. So what's really the proportion, percentage, or maybe amount of the feature that we want to have in our final solution as we run the analysis with a tool like prioritizr. Then this is an interesting component, which is essentially adding another dimension onto a fairly simple problem of I have planning units, I have features, and how much of the features do I need across the planning units? And now that kind of additional dimension would be zones. And so this one is really meant to capture the different types of action on the landscape. And so in this illustration here on the right, you can see one zone might be, this is a conservation zone. So there's it's a fisheries example. So there's no take. So you cannot fish in that area. Then there's zone 2, so the pink, maybe it's like salmon, would be a sustainable use zone. So you have some fishing is allowed, but it has a cap on it. So it tries to balance kind of economic use, but also try to balance this with kind of conservation like outcomes. And then in this example, the third zone, like zone 3, would be a development zone. So basically, no restrictions on what can be done in those areas in terms of biodiversity. So you can extract or also modify those areas at will. And so that's really then an extension to the initial thing of where should an action take place, and not being specific on the action, but in the kind of formulation with zones, you add complexity in terms of saying we also allow the user to specify what different kind of actions should be taken. But one cautionary tale that you see on the bottom of the screen is this setup is really data hungry. So you need to have a lot of information to feed into a tool like prioritizr to really make informed decisions or have informed outcomes coming from this kind of setup. Then next, what I wanted to do is give you a bit of an overview of the principles of conservation planning. So it is really important to think about what are the pieces that we feed into those analyses, what are the pieces that we need to consider, and then also then related to what is the data that could support some of those principles. And one crucial one, but also complex one that which we're going to see later on, is the principle of connectivity. So there's essentially two types of connectivity. One is within reserve, and the other one is between reserve. So this one within reserve is when I look at this simple example on the screen. So you have different populations, and let's say this bounding box is the reserve, and you can see that those two populations, they are too far apart to meaningfully connect to each other. But when we have the population spatially close in the reserve, we actually have within reserve connectivity present. And similarly, if we look at the, let's say, the landscape, so we have here like depicted a highway that kind of crosses through that area of interest. And so if we would say protect this part here in the yellow and this other one here, the highway would actually not allow for connectivity between those two, because let's assume the animals that we are interested in, they can't really cross the highway. So this one would not work well. But the example on the right, where we have those places spatially connected without too much resistance, so the highway being a high resistance area, that is then allowing connectivity between reserves as well. And again, as before, there's a bunch of examples. So we just provide a few examples for folks to get started, to kind of get a sense of what are some studies out there that have done this, what kind of data are they using, and how are they using it. So the next component or principle here is the principle of comprehensiveness. So we can again see here the two potential reserves, one with 4 different species and one that only has turtles. And so we can see if we want to have a comprehensive understanding also representation of what's on the landscape. The choice in this simple example would be the place with those 4 different species over the place with just the one species. Again, one example that I really like, it's a global study where this has been done quite well a couple of years ago. So I think it's a really good example and study to kind of look at and get ideas of how folks have done it. The next principle is the principle of adequacy. So when we look on the bottom left here, the goal for us is we want to have at least 3 individuals, or let's say 3 populations of that bird species present in our solution. So what we really then look at too, and that's related to like the target setting that I was mentioning before, we really need to have at least 2 reserves compared to that example with just 1, because if you just have 1 population of birds, that does not reach your conservation goal. It's fairly straightforward, but it's an important one to point out because that's really where goals and targets come into play. Then how do we set good targets? So this one is actually quite a big topic because what it requires is a good understanding of features or often species kind of requirements, and also what's then more on the statistical side or like on the analytical side is, do we even have a good idea of what might be required? And so that example pulled out here is, and we will also see a little medal on the right. So it's like, let's say our gold standard. So if we have good information or good data on a species in a certain area, we can actually say, like, what's the area that's required to have at least a less than 5% chance that in this case, a possum population would be falling below a certain threshold, which it then doesn't make it viable. So this is really probably the best available data you could get, but also most likely the hardest one to get to. The second one, which is we still lump it into the gold standard, but it's a tier down, I would say, is trying to estimate those kind of targets by asking experts in the field and the area to really make sure that whatever we set as a target is having meaningful representation for the species to allow long-term viability into the future. Then next one is like, which we often have to revert to, is maybe there's IUCN red list criteria that we can set targets based on those. They might not be specific to our specific area, but they're probably the best we can have. And then the last one, it's really we don't have much information on the species in that area or generally, but we have things like the HE targets or now the coming Montreal targets of 30% of, say, the area. And so we could say, if across all the species that we would investigate, we do 30% of all, maybe that represents them in a meaningful way to get to 30% of the landscape. I know it's a stretch, but that's kind of often the starting point if we don't have any of the kind of ways to set good targets up top. Then, as I mentioned before, it's always about good data. So what data do we have? What kind of data can we generate, or what can we rely on? And there is varying degrees of availability for data across the globe. But some of the kind of modeling that has been done is, at least in our opinion, decent enough that you can you use it as meaningful targets or target proxies, at least in analysis. Then this next principle it's the principle of representativeness. So this one is really it's an interesting one because it's really trying to say don't just focus on say like a level of biodiversity. So I have pretty much only talked about a species, but now we're also talking about all levels of organization. And so for me, that's a good kind of reminder of, sure, I usually stay in the middle because species is the type that I'm most familiar with. But we also should consider everything from ecosystems to gene level really. And of course that means more data and more complexity, but it's a good reminder to, if we want to look at representativeness, we need to often go beyond a species focus. Then next principle would be the principle of efficiency. So in this example here, it's just a toy example of saying the reserve on the left, maybe it's because it's slightly smaller, costs like one pile of money, and then the one on the right costs four piles of money. So to have an effective, efficient reserve system, you actually want to minimize your expenditures, but also minimize potential conflicts. So it's really in the face of competing interests, like what's the minimum kind of effort or resource requirements that you can implement to still meet your targets. Oops, sorry. So for this, the efficiency component, and this one is not a new concept, but it's been talked about for, I would say, close to 2 decades now, to really get good cost data for your analysis. But of course, what we often have an issue with is if I, for example, look at some of the work that we have done, if you look at large geographic areas, it's really hard to estimate kind of what would be the opportunity cost or the land values and or so on. Let's say across North and South America, or like even parts of one of them. Then this one, and I would say this is probably one of the ones, like the analytical tools I think are good for the previous pieces too. But to me, this is often one where they really stand out, because like humans are not great at trying to add new pieces to the puzzle in a complementary way. And so what you can see in the example here is, if we were just to look at things in isolation, so we have the green outlined areas, they already have some form of protection management. But then the question is, should we go for this one that's outlined yellow on the left or the one on the right? And if you don't consider those other green ones, you of course say it's the one in yellow on the left there, because there's 4 species there. But if we actually would count or like look at the different species, so what are the different species that we already have protection in place? What we would clearly see is that there has been no protection for the frog species. So in a complementary way, we should most likely go for that reserve on the right, because we would actually add more biodiversity to our reserve system than if we just went for a number of species. So this one is an important component, and there's a number of good studies out there. Again, a few examples there. But this is really from our perspective where like a lot of gains can be made. And so we just have like 3 examples here. There's different ways that those different software packages would find solutions. And you can see in the heuristics, if we just look at this like landscape of potential solutions, it starts from here. So you go, and you go basically to a maximum, or like the highest point in the landscape, and you get stuck with the heuristic, and you don't know if you should go down again to maybe go further up, which is then an improvement with the meta heuristics, because there is also the possibility of accepting less than optimal solutions for a while, at least, or in the beginning. And so that could lead you to a more or closer to the global optimum solution. The issue that both of those approaches have, although, is we don't have an estimate of what is the best possible solution. And that's where linear programming or interlinear programming is really coming into play, because when you implement an approach like that, that's also what we do in prioritizr, you can actually get an estimate of your best solution. So you know every step of the way how far you are from it, and you can actually let the algorithm go as close as you define to an optimal solution. So this one is really allowing us to explore the possible solution space more effectively, or like more comprehensively to really get us to the point where we can be confident that this is mathematically the best possible solution we can get. And so this one is really then getting us into the toy example of looking at some math. And it's just a very simple thing to walk through terminology. And then the next thing I'm going to do, I'm going to actually walk you through a toy example where it's an application to conservation. So this one here is like a mixed integer linear problem. And we have a few of the terms we need to define. So the model sense, like overall, is we want to minimize something and we want to minimize the objective. So the objective you can see, that's the first row here. So we want to minimize those numbers. But we also have constraints we have to deal with. And so the constraints, they actually are components in that they have, in green, you have the coefficients on the left. Then you have the sense, so greater than equal or greater than or equal to or smaller than. And then you have the right-hand side, which is the blue, which then combined make up the constraints. If we then step down to the next block, we have another bunch of components where we have the variable type. So that's in yellow here. Then we have the upper bound of that variable in question, and we have the lower bound. And the possible kind of variable types would be continuous. So it's the C in here. So and then the bounds you can see between negative and positive infinity. Binary is really between 0 and 1, or like 0 or 1, sorry. And integer, it's just integer numbers. And then the last bit, and that's the bit that we usually are interested in, is the solution. So you can see 0, 1, 1, 0 means not the first one, but the second one and the third one, and not the fourth one. And so if we apply this concept to a example for conservation planning, so what we want to do is we want to use the minimum set formulation. So it's saying we want to minimize the expenditure, if you will. The objective is we want to have the minimum number of islands with the constraint of we want to have sufficient habitat for each, which means we want to have at least one population per species in our solution. And the decision is it is like an island is either either a reserve or it is not. And so this is it's a fairly small example, but I think a good example to just walk through and show you how prioritizr works under the hood. So we have those islands. Now we want to do is we just number them, and with those numbers we can then set up our kind of matrix that I showed you before in the toy example. So each island has a number. We have the numbers on the bottom, and so now we can start going. So the first thing we do is define our variable type, define our lower and upper bounds. So again, it's either selected or not, which makes it a binary variable, and the lower bound is 0, the upper bound is 1. So far, fairly straightforward. Then next piece is for simplicity, we just say each of those islands to put into some sort of protection or create a reserve, it's going to cost 1 unit of expenditure. And the objective is really to minimize that expenditure cost. And now we get into the constraints. And so when we set up this constraint matrix, we just transpose the values from island 1 into our matrix here. So you can see there's 1 butterfly population, 1 crab population, and then we do the same for island number 2. So there's only 1 crab population. And for island 3, so we have 1 penguin and 1 sheep, and so on. So this is then the complete setup here. And then what we want to do is we also want to say for each of those features, so those are those animals, we want to have at least 1 represented in our final result. And if we go ahead and then now let prioritizr do its thing, and prioritizr connects to one of the solvers that we support, it crunches numbers, and then your result is that it should select island 1, island 3, and island 7. And so that's fairly straightforward, simple example. But even for that small example, we can go complex quite quickly. So first is we are counting for existing conservation areas. So what you can see now on the bottom, those yellow parts would be that island number 2 and island number 7, they're actually already in some sort of protection. So our lower bound is actually not 0 anymore, it's now 1. So this one means it has to be in the solution. Then, as you can imagine, it's not going to be the same expenditure for each of those islands. So there's no variability in the expenditure, which means our efficiency has to, numbers need to change too. So now we actually adjust which expenditure we have to incur for each island. Then the next piece is there's also not just one homogeneous population of a species across. There's actually, for example, the crab species is a nice one because we have crabs on many of the islands. There's different population numbers, if you will. And so now, in addition to that, we also have different targets. That's the right-hand side, or like all the way on the right of the screen. So we have now different targets for different species or different features, which we want to meet with the constraints that we're setting. So all those components, they are making things more complex, but they're still fairly straightforward, let's say. Now where the thing really gets complicated, because if we would account for connectivity in a straight up way, it would be going or like diverting from linear. So we actually have to find ways to linearize the problem that's actually quadratic. Anyways, I'm gonna just walk you through a bit here. It's really just for illustrative purposes to show that even if we start with just 2 of those islands that we're considering, it already gets a bit complicated. So let's just consider island 1 and 2, the connectivity between the 2 of them. So what we have done here in the purple and yellow. So yellow, we are saying we have an exponential decay inverse, an exponential decay related to the distance. So it's 1/5 because it's 5 kilometers. The purple component now is we have to make a connection between the cost unit and the connectivity unit. And so what we are saying is 3 connectivity units equals 1 cost unit. So that's why we have 3 times 1/5. So that's the maybe more straightforward part. But where it gets complicated or more complicated is how many constraints do we have to take into account. And so now what you can see, we're actually adding 3 rows of constraints. So 1 for island 1, 1 for island 2. So basically the variable for island 1 and 2 being selected can only be true if island 1 is selected. So that's the first row. It can only be true if island 2 is selected, so it's the second row. And it's also true that 1 and 2 need to be selected for for 1 and 2 to make sense. But what we can do, we can actually remove this third one because of the setup we have. But what that still means is, what is just that one connection between those 2 islands. We have 1 additional variable with 2 additional constraints. And in our simple example, that's maybe manageable. But then if you look at the bottom right here, you can see how the complexity of a problem is just exploding. Because if we imagine a problem with about 1,000 planning units and connectivity between all of them, we actually having to deal with about 500,000 extra constraints. So it's from a computational perspective, that's going to be a huge difference. So with that in mind, now going over to prioritizr and like kind of what we actually tried to do. So we tried to capture, pardon me, the components that I mentioned before, but also make it let's say more accessible than what we have had available to us before. And the big part was it should be a sort of human readable code. So it should be maybe more straightforward for folks to actually get started with this problem formulation, but also reading them. Design the problem that you want to solve. And the third piece, which is taking advantage of some of the solvers out there, solve it fast. And so what we have is that the workflow is really mainly the data component. So lots of work usually goes into finding the data, finding the right data sets, but also having ways to make the data kind of setup not too cumbersome. So there's a lot of helper functions in there too. Then the problem formulation. So all that setup we did for what's the objective function, what's the constraints, and also on like that. Also wanting to make it flexible, but also fairly straightforward. And then setting parameters for the solvers that you might want to use. And we're trying to support as many solvers as we can. So I think currently we have like 7 different solvers that we support. Then ship everything off to the solving engine. That thing hopefully solves the problem. Then bring back the results and generate maps, statistics, and outputs from those results. And so this one is really where prioritizr comes into play. So it makes the whole setting things up, letting things run, and then analyzing things hopefully way more straightforward. And then it's like loop back and maybe adjust as you go. And so what I meant with the mental model and human readable code. So what you can see on the right, that's really what from the setup that I showed you before, that's what you could do in your head. So it's like we have some data, we have objectives, penalties, constraints, and so on. And if you look at the at the code on the left, that's really then how the setup is in prioritizr. So it's really meant to match the mental model very closely. So we actually have a good way for people to read, and it's a lot of it is actually from the ggplot2 folks and the grammar for graphics. It's very similar if you're familiar with that component in terms of how the code looks. And then one component too. So we keep doing benchmarks to make sure that the different solvers that we support, that they're working, but also that we have a sense of kind of what's reasonable, what's doable for, like especially comparing the commercial and open source solvers. So we have the ones in red and orange. So it's Gurobi and IBM Cplex. Those are both commercial ones. They are free for academics, but for folks like me in like NGOs, that's a consideration because usually you would have to pay for using them, and then it's important to show trade-offs of what it means to use open source solvers compared to the commercial ones in a setting like ours. Speaking of getting help, so there's the prioritizr website. So we have tried really hard to make this as user-friendly as possible. So if you're new to this package, as you go and explore, if you choose to, please have a look. And if you find anything that doesn't make sense, it's kind of, oh, I don't quite get this thing. We're always happy to hear feedback because we always try to improve the documentation. And what we have in terms of documentation is, so it's a website, there's descriptions of all the functions that we have in there. There's also tutorials and worked examples in there, which one of them I'm just going to walk you through in a minute. And we have workshop materials and such too, to really help get you started with the package or get you more comfortable with the package. And again, like as I mentioned before, lots of the citations in the slides, they are hopefully helpful too. And then just on the bottom there's free, what we think good books, I mean different topics slightly, but good books to kind of get more in-depth understanding of maybe some of the methods for systematic conservation planning, but also then data science and especially data science in R that might be helpful to you too. And with that, I'm actually gonna switch over to my R session and just walk you through one of the articles that we have on the prioritizr website. So I can also paste this link in the chat as well. But it is really kind of, it's the code extract from what we have up there. So if you look at I can actually show you this too. If you look at the website, you are gonna see that the getting started section here is really what I'm just gonna walk you through quickly. And what you see in the documentation here, there's more kind of comprehensive description of what you actually see and what's happening. But it's just for that I'm gonna go through this example to just get you started if you choose to. So first, just loading packages, fairly straightforward stuff. And then next piece, we're actually gonna load our planning unit data, and this one is one of the example data sets that prioritizr actually ships with, or we have a helper package where there's bigger data sets too. And it's a fairly common data set for systematic conservation planning in general. So it's from Tasmania, so that's TS. And so what we can do, we can actually have a bit of a look at what we have in that. In this case, it should be a shapefile, yes. So you have like IDs, you have the cost, you have whether it's logged in or logged out. So this is an important component too. When I mentioned before, if a location is part of the reserve system already, that would be logged in. But there's also the possibility of there's some places that we just can't do anything in terms of conservation, but it's important to keep track of them because there might be biodiversity or feature data on them. So it is for accounting purposes mostly to make sure that this is also captured. And then we have the features, and so we did the print. So this next thing is, because we have some information on whether a protected area is already established, we're just going to set the cost of this place to 0 because we don't really want to account for it because we know it has to be taken into account anyways. And then next thing, just a visual on the planning unit costs. So you can see the ones that we just set to 0, they are now in dark blue. And then the higher the cost, the kind of more into the yellow the color goes. Then next bit we're gonna plot is, so which areas are already having some form of protection. So in this case, you can see all the parts on the map that you see in yellow. And then next we're gonna just have, let's minimize this again. Then we can see there's a total of 33 features in this dataset. So there's different features, and I'm just gonna plot 4 of them. So let's see here. So yeah, there you go. There's 4, in this case it's species or ecosystem types too. And you can just see there's an example representation of 4 of the features that we're using. And so now here we're coming to the prioritizr related components. So I'm just going to highlight this part here. So this is really the R code that's hopefully fairly close to the mental model. And so we're going to set this up. And so now prioritizr is doing its thing, setting everything up, and then we can use the print command. So this is just giving you a bit of a sense of what is the data coming in. So we can see through here, what's the data coming in, what are the planning units, what are the cost data, and it actually gives you a nice summary of what the cost values vary between. So it varies between 0 and like 62. So you have a nice way to kind of show what am I dealing with and have I set things up in a way that makes sense. So this is a nice way to get a quick summary of what's the problem that you have set up. Then the one piece of information that I put in here that if you run this for the first time, you actually need to install a solver. And so that's what I mentioned before, but the question would be open source solvers, commercial solvers, but also in each of those groups, there's variability too. So it's really then trying to figure out what is a solver that works for me, what do I have access to, And then what we also do, I'm just going to show you this quickly, is what are the solvers that we currently support. So as you go to the website with the solver, so the link is in the, so I should make this bigger. The link is in the R code too. So you can see the different solvers with Groovy, Cplex, and so on. So there's a number of solvers that are supported that you can choose from, and depending on your operating system, so Windows might be a bit trickier for some of the solvers than others. So it then depends on what makes sense for you and what works for you. So having figured out the solvers, we can then actually say, I'm happy with the problem. Everything looks good from the print statement. So now let's actually go ahead and solve this problem. So this one, it's solver specific output that you can see on screen. But what you basically just see in this case, so you can see I've used Groovy for this example because it's quick, but it's then giving you some parameters about the model it's trying to optimize. You can see that the model size with how many rows and columns and how many non-zero values and so on. And then if you have verbose like outputs, they can actually see what it's doing in terms of closing the gap that you set, and eventually get to an optimal solution. So this is quite useful as you get more familiar with prioritizr and some of the solvers, because then you can also verify how fast it's running and like if it's actually getting anywhere. So that's maybe more advanced, but for our purposes now, let's just say finite got us a solution, and now we're just going to look at this. And so you can see the prioritization outputs. I mean, you would recognize a lot of it is similar to what we had in yellow before with the logged in components or those already protected areas. But you can see then the output there. And what we do next is we actually want to calculate like how much of the features that we have. So I'm just going to show you this quickly. How much of the features that we have is already protected or has its target met in current protected areas. And so what we have here, there's this one column in met. So it's a binary saying true or false. So it's an easy or hopefully easy way to just do a quick verification on it has it met for number 1, number 2, not number 3, number 4, 5, yes, but not number 6. So to have an easy check on looking at current protected areas, how well are we doing? And then we can also look at this across. So this one, it's not surprising now that all of them are met because our problem setup has actually said, meet me all my goals or like targets. And so this one is also verification on, yeah, it has met it, so it's good because that's what we told it to do. But then going back to the protected areas, one thing that we can also do is get a bit of a histogram going in terms of how much of a feature is actually covered or protected by those protected areas that are already in place. And you can see there's some that actually reached up to 100%, but some of them are fairly low. And then you have a maybe more equal spread across like percentages up to 60. So you can see a bit of variability in terms of how much do we already have protected or set aside in the current protected area system. And so what's often what this is often used for is a gap analysis. So basically, how close to reaching our targets are we with the current system? And then for the gap component, that's where tools like prioritizr come into play. So that's again like just a few of the statistics and what you can output to, and then you have your summary of what we do when we go from the current protected to the output of prioritizr. So this is another example that's I think well described in the documentation to just also help you go through like what is actually the case from protected to now prioritizr outputs. And then maybe next piece we can do, that's just a quick example too, is the relative importance. What you can see when we look at this, that's also one of the reasons why I used Gurobi now. You can see there was actually quite a few scenarios that it ran. And the reason why we did this was we wanted to actually let like prioritizr investigate the solution space more broadly. And so this one is a good example of why we did this. So we wanted to say, don't just stick with the one optimal solution, because often in like a practical sense, if you look at what actually happens on the landscape, just having one solution is not going to be good enough. And so what we do here is, so we run, and then there's different, like this here, there's different importance evaluation functions that we have. And again, like if you want to find out more, have a look at the documentation to really help us understand across this landscape. So this one would be Tasmania. Like, what are the places that are really vital to focus on? Because especially if the problem is bigger and there's a lot of potential options, or like a lot of options, choosing the first ones to work on is tricky. So this one is really meant to help get a better sense of how important are those individual like planning units to actually move conservation forward. And what you can imagine, what's often the case is, if you have a species that has a small range, and it's only found in that small range, you have to essentially get a planning unit, or maybe several planning units from that area, in order to make any progress, or have any chance to have that species be sustained to the future. So that's kind of one of the pieces that we could think of there. And so then the last bit that I'm actually going to show you is something that's similar, but instead of looking at importance in the way that we just did, we actually now looking at a portfolio. So basically, a bit dependent on the solver that we're using, we can actually either take advantage of the solver internally storing information on the steps it's taking, or maybe we have to kind of brute force running it again, but with a different starting point. And so what we do here is we're saying, take the first problem that we put together, and then add a portfolio. So in this case, we're saying add the gap portfolio. Then the number of solutions is 1,000. So it's actually run that thing 1,000 times, essentially, or up to 1,000 times. And so what we do now is we go ahead and let the solver, in this case, it's again Gurobi, do its thing, because we just want to get a good sense of kind of what's the solution space out there. And so that's why we chose to say, if we run like 1,000 solutions, that's probably enough experimentation to give us a decent sense of like what's the space that we're looking at. And so we have done this. There's probably not too much sense to really go into details of individual ones, but I just wanted to quickly show you this piece. So there's a total of 1,005 columns. So you just remove those first couple, and then you can see it starts solution 1, 2, 3, and then goes on. So that's really one column per solution. And that's really what we want to do. And what we often then look at is kind of what's a reasonable way to visualize this 1,000 solution space. And so what we do is, you can see down here that we just do a cluster analysis. So we are just trying to make sense of how similar are the different solutions, and kind of what can we gain any insight from this space. So this is just the cluster analysis outputs like visualized here. And so what we want to do is we actually want to look at some of the kind of most central, if you will, results for those components to really get kind of maybe a visual sense, or maybe can then do some further analysis further on to help us understand what are those different clusters. So with the code that I just let it run, we can see that there's those 6 solutions that we have. So with the solution numbers that actually representing the midpoints of those nodes. And then if we look at them spatially, it's gonna plot us those. And in this example, there's not gonna be a huge variation. Like you really have to look closely to see like where some of those green dots, which is the kind of solutions that prioritizr has proposed are. There's some that start to look a bit different in terms of the spatial configuration. Like if you look at this one, there's like no selected parcels in this area here, but they moved over here. So you can see that's kind of the variability that we have across that cluster analysis, and it's really a starting point to then think about maybe groupings across those 6 kind of centroids of the groups, or maybe also think about some further analysis that one wants to do. But anyway, so I just wanted to end with this component here. I'm gonna just show that last slide. And so the slides are available to you. If you have any questions, comments, please either ask now or also reach out through email to me, or if you want to create an issue, again, like I said before, you should try to do like a day turnaround, which so far works pretty well, but really want to be helpful and engaging the community of prioritizr users out there. So with that on, I'm gonna stop sharing my screen and happy to answer any questions if there is any.
Thank you so much, Richard. Let me go to the poll everywhere and check the questions. So the first question I have is, when people say working with zone is data hungry, what kind of data would actually be required?
Yep. So it's pretty much what I've talked to today. It's the same type of data, but it's essentially you need that whole data stack for each of the zones. So then meaning if you have 3 zones, you need the information that I walked through 3 times. So it's not different data types, it's just more data. And then like also often what's happening with if you have specific action types that you're interested in, you actually want to also go into the space of if I implement action, I don't know, like a restoration action, let's say, what is going to be the consequence on one of my features from that action? So it's more granular and also more volume of data.
Thank you. The next question is, can open source evolutionary algorithms, for example, I don't know what this is, but it's called NSGA2, work with this package?
I don't know. Maybe the best thing would be if you just wanna ping me and then we can, because I'm not familiar with that one either. But that's one thing too. It's maybe not specific to that, but one thing that Jeff has worked quite a bit on too is thinking about different types of algorithms that could be implemented or included. So some phenology type thingies, so that there's parts that he has explored, but I think it's easiest to just get in touch with us and then we can figure it out. And if it doesn't yet, maybe we could in the future.
Yes, thank you. Just send an email to Richard. And also the third question is it mandatory to set costs for the planning units? If I don't have information on costs, can I simply put the same price to every planning unit?
Yeah. So this one, that's a really common thing. It's if we don't have good like a good information or good indication of varying costs, that's usually what we start with. It's just the same cost across. So that's a starting point. But also, I think I mentioned probably for the last 2 decades, there has been good evidence on how having like cost information that varies across space is going to be really beneficial. But yeah, we often start with we don't have any information on cost, so cost is just constant.
Okay, thank you. The final question is, how can researchers ensure their prioritization are ethical, given that many applications of these technical solutions in conservation are in region outside of the researcher's home country, especially given global north source biases in funding versus biodiversity? Is there good guidance?
Yeah, so that's one is a big topic. It's because from the tech perspective, it's agnostic to any of those ethical considerations. What we have done, and what other groups do too, is, I mean, speaking about the Canadian context, there is a few examples where I've actually worked with Indigenous communities, and the Indigenous community would drive the process, and then where you use prioritize like a technical level, but it's always just the community comes first, and then the community drives what data goes in, or what are the parameters, what are the goals and such. If we think about larger analysis, because I know lots of people like apply those tools across vast geographies, it's tricky. Like it's what we have done a bit was kind of try to, and it's usually broad scale, like try to incorporate at broad scales, like different land tenure types, or also different kind of scenarios on what might happen. But it is when those tools are getting closer to being applied to, like, say, the ground, or like in a real setting, it is crucially important for like organizations like ours who work on the ground to work with local communities, stakeholders, right holders, to ensure that this all makes sense. So it's guidance wide. I don't know if there's much out there for broad guidance, but it's, again, for the Canadian context, it's trying to work like in a space that respects land and right holders. But I don't know if there's any broader guidance really.
Okay, thank you, Richard. That's something we should work on for the next few decades. And in your opinion, sorry, there's two more questions come up after the refresher page. So,
Mhm.
first question is, in your opinion, how does systematic conservation planning compare to structured decision making? And the second question is more technical. Could this be used for riverine restoration management, where the spatial units are river units?
Yep. So that the second one, that like if I answered it first, that yes, it's a, again, it depends on the data, but what we do too is like when I mentioned the connectivity piece before, like this one assumed non-direction connectivity, so like connecting in any way the same amount. But we also have direction connectivity, so especially for river systems where we know like upstream and downstream connectivity are two different things. So that one is definitely something to do, and there's several good examples in the literature too where this has been done. With the first one, it's an interesting question too, and it's for me it's a quite important one, because when I first started to work for so I come from academia, but then I started for working for an NGO. And what we've tried to do is, coming from academia and trying to kind of push as much of the kind of cutting edge stuff that we can do. And so it doesn't really matter if it's a systematic conservation planning to structured decision making. It's kind of in the same kind of vein. But what we were kind of realizing quite quickly, which is good, is when I, for example, talked about the different zones or the prioritization with zones, just introducing the concepts that I've done today was such a stretch for the staff working in our organization, that we quickly realized that if we go too quickly or want to push it too far, because we did systematic conservation planning, then we tried to do the planning with zones, but then we also tried to push value information of information components on this too. So basically increase complexity. It just did not work. So it is really important to understand the audience, so they can understand who you're working with, and then also just going as fast as any like that group wants or can go. Because otherwise, if we try to push too hard, and it's been a couple of years, it just wouldn't have worked. But it's I think for systematic conservation planning and structured decision making, I think it's kind of the same space. I know we separate pieces, and there's, at least from the academic side, a lot of nuance. But to me, it's always very important to think about what is kind of the ultimate outcome, and also who are you working with. That is especially coming from the academic space, where we usually often just try to push kind of the boundaries of what we can do to making things more realistic. That was a big eye opener for me.
Okay, thank you so much, Richard. I think the final question is a bit technical. So they're asking,
Mhm.
how do you transform species distribution models or connectivity into categories in your package? Is
Yeah.
that something? Okay, okay, yes.
Yeah, so this one, so when I think about, I mean, either of the data sets, so there's different ways to include those. So when I think about continuous data, you can use continuous data straight up. So if you have species distribution models or species abundance models, which I like quite a lot because it's an easier one to think of. If I have abundance models, then I kind of represent either relative abundance or true number of individuals. So that one can be used straight up. What folks also have done is, um, let's say, use the species distribution model that is a range or like a continuous variable, but also turn it into a binary. So it's saying a yes or no. And then it usually just depends on what's the setup, what's the constraints that you work under, and kind of what's really the goal of the analysis. But a big component is really that prioritizr itself can take continuous data, binary data, and categorical data. But it depends on kind of what the question is. But it is really meant to be flexible to allow you to put as much information in it as you can or as it is useful. So there's also, yeah, because there's something mentioned about the manual. So there is documentation on kind of what features we will put in. And if you, as before, like if you can find something or so, just reach out to us. Either do it through GitHub with an issue, but if that's not what you usually do, just shoot us an email. So it's usually myself or Jeff, and like his information should be on there too. We're always happy to help. But that is a really common thing to do because I know historically we tended to convert continuous data into binary data, but we don't have to do that anymore. No.